So, hello everyone. In our last lesson, we learned about Einstein's photoelectric equation, that is Kmax equals to HF minus W. So today in this lesson, we will learn about the experimental method to investigate this relationship, Einstein's photoelectric equation, and plot an experimental value of maximum kinetic energy versus frequency, and relate the slope and x-intercept to the formula of Kmax equals to HF minus W. And we will also end off by trying some questions. Okay, before we start with Einstein's photoelectric experiment, let us reflect back about this exercise 2, right? If you refer to part 1 of this photoelectric subtopic 3.2. So in exercise 2, we had this example, right, where the electron comes in with 1.2 times 10 to the power of negative 17 joules of energy. So the electron comes in and it moves between these two spaces, right, that is created by two parallel plates towards point A. But point A is placed at a negative potential. So the question is, what is the potential required to stop the electron at point A? Okay, as the electron approaches point A, the electron is slowing down simply because the electron is negatively charged. And this plate or point A is also negatively charged. So since they are both negative, they will repel one another. So the electrons will slow down, all right? So if you refer to example 2, we can find by using the law of conservation of energy, if the electron comes in with 1.2 times 10 to the power of negative 17 joules of energy, they're actually coming in with 75 electron volts of kinetic energy. So what's the potential required to stop electrons with 75 electron volts of kinetic energy? I would require a potential of 75 volts. So this is known as the stopping potential, the potential required to stop the electron at a certain point, in this case, at point A. So if the electron comes in with 100 electron volts of kinetic energy, what's the potential required to stop the electrons at point A? So the answer will be, I will require 100 volts of potential to stop electrons with 100 electron volts of kinetic energy. Okay, once we understand this example, right, we can go and investigate Einstein's photoelectric equation. So in this experiment, right, you have a photocell. So this is your photosensitive surface, right? And this is your collector. So this photocell is connected to an emitter. So when light shines onto the photosensitive material, electrons will be ejected. So when electrons are ejected, they have kinetic energy. So they will move towards this collector. So when this electron moves towards this collector, they complete the circuit, right? And then back and where it started off again. So you can measure the electrons that move, right, by setting up an ammeter in this case. So when electrons move, it will be indicated by this ammeter. So to find what is Kmax, we apply a negative potential. It's similar like example 2. The electrons are moving from here to here, right? They are moving because of the fact that they absorb the energy of the photon and they have kinetic energy. So it's like this case, the electron is briefly moving. So we want to find what's the potential required to stop the electron at a certain point. In this case, this is point A. We want to stop the electron at this point. So to stop the electron at this point, we make point A at the negative potential. So we connect it across a battery to the negative terminal of the battery. And the positive terminal of the battery is connected back to this photosensitive material. So when we connect it like this, right, you find that the electrons find it difficult to move towards point A because point A is now negative. Okay, if the potential is 0, you find that all electrons move towards point A, irrespective of their kinetic energy. The high energy electrons move to point A, low kinetic energy electrons move to point A. So that's why the current is maximum. So when the potential is 0, current is maximum. So when I increase this potential, the negative potential, right? So you see I'm increasing the negative potential. At the same time, the current reduces to zero. Okay, what is happening when I increase this, make this more and more negative? So when that happens, the electrons that are negatively charged particles will basically, from the law of conservation of energy, would lose kinetic energy as it moves towards point A, because point A is at a negative potential. So much so, some electrons do not have enough energy to reach point A. So if they do not have enough energy to reach point A, they are not registered by your emitter. So that's why your emitter gradually reduces to zero. So there will come a point when the current is zero. So when the current is zero, this implies that the potential of point A is so high that even the highest energy electron, the electrons with Kmax, cannot make it through. So this is known as a stopping potential. So the stopping potential in this case will be about 4.2 volts. So when I shine violet light of frequency f1, when my current is zero, I record the potential from my voltmeter. So in this case, it gives me 4.2 volts. Then I repeat the experiment. I use a different color light, like blue light. So blue light has lower frequency. That means the photons have lower energy. So again, the electrons will absorb this blue photon and they'll be emitted. So again, take note, when the potential is zero, current is maximum. Next, when I increase the potential, the current will reduce, right? So once I say this is current is zero, I record this as my stopping potential. So my stopping potential will be 2.8 volts. And then I repeat for different color, green light. I do the same, right? Expose the photosensitive material to green light. Photoelectrons will be produced. Current will be maximum when potential is zero. So when I increase the negative potential, then the current reduces until it becomes zero. So once this is zero, record the reading on your voltmeter. This will give you your stopping potential. So depending on the frequency of the light, the higher the frequency, the higher the stopping potential. So what we do now will be, right, to plot the graph. So to plot the graph, we use a theoretical formula that is Einstein's photoelectric equation, that is Kmax equals to HF minus W. Kmax will be the maximum kinetic energy of the photoelectrons, which we can actually find from the stopping potential. So if I use frequency f1, I have a stopping potential of 4.2 volts. So in other words, my Kmax will be 4.2 electron volts. So what I do is I write this in the form of y equals mx plus c. So what I plot along the y-axis will be Kmax. And what do I plot along the x-axis will be the frequency of the light. Right? So Kmax in terms of electron volts and frequency. So for frequency 1, I know the stopping potential is 4.2 volts. So in other words, Kmax will be 4.2 electron volts. Then I do for frequency 2, stopping potential is 2.8 volts. So Kmax is 2.8 electron volts. And so on and so forth. So I plot for multiple frequencies, and then I plot a graph. So the graph will be a straight line, right? That doesn't pass through the origin, because C is not zero. Okay. Instead of plotting in terms of electron volts, right, I can also plot Kmax in terms of joules, in terms of, right, joules. So how do I convert electron volts to joules? So how do I convert 4.2 electron volts to joules? I just times or multiply with the charge of one electron, that is 1.6 times 10 to the power of negative 19. So I convert it to joules. Right? So when I find the gradient of the specific line, right, this will give me Planck's constant. Because you see, my y-axis is Kmax, my x-axis is frequency. So the gradient of the graph will give me Planck's constant. what would my y-axis intersection give me? Yes, it will give me the work function of the metal. And my x-axis intersection will give me the threshold frequency. The threshold frequency is the minimum frequency of radiation below which no photoelectrons will be emitted. Okay, so now let's try some exercises, right? For a particle metal surface, it is observed that there is no minimum frequency of light below which photoelectric emission does not occur. So this observation provides evidence of a particular nature of electromagnetic radiation. So state 3 further observations from photoelectric emission that provides evidence of a particular nature of electromagnetic radiation. So you see, right? To show that light is a particle, there are certain experimental observations that we can make, right, from Einstein's photoelectric equation. One of them is there is a certain minimum frequency of radiation. So this implies that light is a particle. So besides this minimum frequency, what are the evidence to show that light is actually a particle? So pause this video. Okay, what are the evidence would be basically, right, there's no time delay between illumination and emission of photoelectrons. The moment you expose the photosensitive material to light, you illuminate it, instantaneously photoelectrons will be emitted. So this instantaneous effect shows that light is actually a particle. Like when a ball collides with another ball, instantaneously the other ball that is initially at rest will start moving. Okay, the next one is kinetic energy. Maximum kinetic energy of electrons is dependent on the frequency of radiation. So the higher the frequency, the higher the kinetic energy maximum. The next one will be maximum kinetic energy of the electron is independent of intensity. Okay, based on the wave theory of light, the intensity, right, will determine the energy of the photon. So if I shine, let's say, infrared photons to a photocell, nothing happens. So if nothing happens, I just have to increase the intensity of the light, infrared radiation. But from experimental evidence, right, it shows that even by increasing the intensity, photoelectrons will not be emitted. So energy is not dependent on intensity of radiation. And finally, right, the rate of emission of electrons is dependent or proportional to the intensity. This is provided that the frequency of radiation is greater than threshold frequency. This is referring to whenever the frequency of radiation is less than threshold frequency. By increasing the intensity, nothing happens, right? Okay, rate of emission will be how many electrons will be produced. If there are 3 photons, then there'll be 3 electrons produced. If there's 3,000 photons that you supply, then there'll be 3,000 electrons that's be produced. So the rate of emission, the number of electrons produced, is proportional to the intensity. Because Einstein explained that intensity of the photon is related to the number of photons. Okay, exercise number 5. Explain why emitted electrons have a range of kinetic energy ranging from 0 to a certain maximum. Okay, pause this video. Okay, to explain this, let's look at this energy diagram, right, of the electrons inside the metal. So the electrons can have any amount of potential energy up to a certain maximum. So in this case, right, let's assume that the electrons can have a maximum potential energy of 3 electron volts. And let's assume that a photon comes in. So this photon has 5 electron volts of energy. So if this electron that is having a potential energy of 3 electron volts absorbs this photon of 5 electron volts, so this electron is going to use part of its energy to overcome the work function or to overcome the forbidden region. So how much energy is it going to use? It's going to use 3 electron volts to come out. And the balance will be in the form of its kinetic energy. Okay, let's assume another electron. Let's say, for instance, this electron that's much deeper inside the metal. And this electron has a potential energy of 4 electron volts. So this electron can absorb this photon. So if this electron absorbs the 5 electron volts photon, it's going to use more of its energy to come out. It's actually going to use 4 electron volts to come out. By the time it comes out, it has an excess of just 1 electron volts of kinetic energy. Okay, an electron that is deeper inside, let's say, for instance, this electron, which has 5 electron volts of potential energy. So if this electron absorbs a 5 electron volt photon, it's going to use all its energy to come out. So by the time it comes out, it has 0 kinetic energy. So this would explain why the electron comes out with a range of energy from 0 up to a certain maximum. So the answer is all electrons in the metal do not have the same potential energy. It depends on how far deep they are from the surface of the metal. So when the photon interacts with the electron absorbs the energy of photon and uses part of the energy absorbed to gain potential energy to overcome the forbidden region. And the balance of its energy will be its kinetic energy. Right? Okay, let's try this exercise 6. All right, pause this video. Okay, in this question, the stopping potential of the photoelectric cell is 1.10 volts. So yellow light of 570 nanometer falls on the photocell. So in part A, right, what is the maximum kinetic energy of the photoelectrons emitted? And B, what's the work function? And C, what's the threshold frequency? So Kmax can be found from the stopping potential. So remember, the stopping potential is 1.1 volts. That means it can stop electrons with a maximum kinetic energy of 1.1 electron volts. So Kmax will be 1.1 electron volts. So convert it to joules. So often, right, you see electron volts is just a convenient way of representing energy. But whenever we have to use energy in our calculation, we have to change it to SI MKS units. So the SI MKS units for energy is in joules. Okay, so for B, determine the work function of the metal. Okay, this is where we apply Einstein's photoelectric equation. So we know Kmax, we know the frequency of the light, because we are given lambda. So we know the frequency of the light. And we know Planck's constant. So by substituting into this formula, we can find the work function of the metal. So this is where it's important to change energy to joules, right? From electron volts to joules. Because if you don't do that, because this is SI MKS units minus electron volts, which is not possible. So Hc over lambda will give you SI MKS units. Energy has to be in SI MKS units as well. So from here, the energy of photon minus the work function, or Kmax, this will give you your work function, 1.73 times 10 negative 19 joules. Okay, if I want to convert the work function to electron volts, I just divide by the charge of an electron. Okay, for C, what's the threshold frequency of this metal? So to find threshold frequency, we set Kmax to be 0 from Einstein's photoelectric equation, right? By setting Kmax equals to 0, that means the frequency of radiation is the minimum frequency of radiation. So the frequency minimum of radiation is basically equivalent to the work function of the metal. So since we got the work function, we can find the threshold frequency. So work function divided by Planck's constant will give you the minimum frequency of radiation. Okay, next question. So pause this video. Okay, so in this question, a certain metal has a work function of 2.30 electron volts. So when a certain light falls on the surface of the metal, electrons with maximum speed of 6.49 times 10 to the 5 meters per second were observed. So determine the stopping potential, B, the threshold frequency, and its corresponding momentum. Okay, so to answer this, maximum kinetic energy can be found because we know how fast electrons are moving. Kmax, right? So we know what is Vmax, maximum speed. So using this formula, we can find that the kinetic energy maximum will be 1.92 times 10 negative 19 joules of energy. So what's the potential required to stop electrons with this amount of kinetic energy? So what we do is, from the law of conservation of momentum, right? We need to have a potential. So what is the work done by this negative potential in order to stop the electrons with 1.92 times 10 negative 19 joules of energy? So you can find delta V. So delta V will be the kinetic energy divided by the charge of one electron. So this will give you 1.20 volts. Okay, so for B, right, what's the threshold frequency? So for threshold frequency, again, we said Kmax equals to 0. This is your Einstein's photoelectric equation. We said Kmax equals to 0. So the threshold frequency, which is equals to the work function. So threshold frequency is work function divided by h. So we know h, we know work function. We can find the threshold frequency. And finally, what is its momentum? What's the momentum of this photon? So momentum is actually h over lambda. But what we need to know is, first of all, what is lambda? So we know the threshold frequency, we know the speed of light, we can find the lambda of this wavelength. So once we know the lambda, we can find its momentum, because momentum is h over lambda. So h divided by lambda will give you the momentum, which is 1.22 times 10 negative 27 kilogram meters per second. All right, so in this part, we learn about the photoelectric experiment to investigate Einstein's photoelectric equation. We plotted the graph and we analyzed the graph. There are three important things that you can get from the graph, mainly Planck's constant from the gradient. The y-axis intersection will be your work function. Your x-axis intersection will be the threshold frequency. And we also tried examples of how we apply Einstein's photoelectric equation.